Welcome to a new segment of our FHinfinity Quick Tour series. In this video, we'll explore the FHanalyzer module. Beyond the core FH simulation environment, FHinfinity includes two additional workspaces, FHanalyzer and FHExtra. FHanalyzer houses a suite of specialized tools, two for pre-simulation analysis, two for post-simulation validation, and two sensitivity meters for parametric studies. Importantly, all these tools are dynamically linked to the main simulation model, meaning they can both import data from the model and push results back to override the base case when needed. Let's take a quick tour of the first tool, the Combustion Analyzer. This module enables standalone combustion calculations, no full heater simulation required. Once executed, results are displayed directly within the analyzer, including flue gas composition by mass and volume %, dry and wet basis, fuel properties such as lower heating value LHV and WAV index, detailed breakdowns of combustion air requirements and flue gas characteristics. A valuable add-on feature is the built-in efficiency calculator. This tool estimates thermal efficiency indirectly without needing heater geometry or detailed coil data. You can either input a measured flue gas temperature at any point in the heater to calculate heat absorption, or provide a target absorption to back-calculate the expected flue gas temperature. This calculator is especially practical for validating daily operational data. For instance, when field operators record heater efficiency using portable instruments like testo analyzers, this tool lets you cross-check those readings against model predictions quickly and with high accuracy. The next pre-simulation tool in FHanalyzer is the burner simulation module. Here, simulation refers to generating a capacity curve for gas-fired burners. Based on your specified fuel gas conditions and burner tip details, the tool calculates the precise capacity curve using fundamental thermodynamic equations. We also include a subcalculator. For each burner, you can specify the number of burner tips, then define the count and diameter of individual orifices. You can even model partial fouling or blockage on burner tips to assess performance degradation. Now, here's a highly practical workflow. Once the capacity curve is calculated, you can export it directly to the main simulation model. From that point forward, instead of specifying heat release via mass or volumetric flow rate, you can input fuel pressure, just like you would monitor in the field, and run the model under realistic operating conditions. Even better, when using the temperature controller mode, you can work in reverse. Set your target process outlet temperature, and the model will calculate the required fuel pressure to achieve it, helping you troubleshoot or optimize control strategies. A quick note, while this tool is primarily optimized for gas fuels, it also supports fuel oil applications using established empirical correlations. And if you have vendor-specific performance data, you can manually input your own characteristic curve for use in the main model, ensuring maximum flexibility and accuracy. Next, let's explore the heat loss analyzer. This module features two distinct analyzers that can be run independently or in combination. The first one focuses on refractory optimization within the firebox and its impact on overall heater performance. While our base model uses a single refractory layer for simplicity, this tool allows you to define up to 3 layers separately for the floor, roof, and both exposed and shielded walls. You can run this analysis using either a fixed outlet temperature optimizer or a fixed enthalpy approach, depending on your process stream phase and operational constraints. Once the solver completes, it presents a comparative report against the base model. This includes changes in fuel consumption, total heat loss, and the specific efficiency shifts in both the firebox and convection sections. It's also worth noting that running this analyzer automatically generates a 4th standard datasheet page, the refractory design sheet. This report details critical thermal data, including hot face temperatures and casing temperatures for the walls, roof, and floor, providing essential validation for mechanical integrity and insulation effectiveness. The next module within the heat loss analyzer is air infiltration, a powerful feature uniquely supported by FHinfinity. In real-world heaters, excess air levels often differ significantly between the roof area and the region below the damper. This tool allows you to model that reality by defining two separate excess air values, letting you observe exactly how these infiltration gradients impact overall heater performance. Additionally, a built-in subcalculator is provided to estimate the mass flow rate of infiltrating air. You can input the total area of gaps or cracks in the heater structure, and the tool will calculate the corresponding air leakage, helping you quantify losses from poor sealing or maintenance issues. Next, let's look at a highly practical tool, the Tube Life Calculator. This module serves two key purposes. First, it can calculate accumulated damage based on the tube's historical operating conditions. Second, by inputting future operating parameters, it predicts the remaining useful life of the tube. The software's internal database includes all alloy materials specified in API 530. For rupture life calculations, you can choose between three basis curves: minimum, average, or adjusted average, depending on your design conservatism and risk assessment criteria. The example shown here is taken directly from API 530. As you can see, FHinfinity reproduces the standard's results with high precision, validating the accuracy of our calculation engine. Next, we move to our first post-simulation tool, the Coke Forecaster. This analyzer uses a corrected Ebert-Panchal model to predict coke formation within the tubes, based on process fluid properties. The rate of coking depends on two key factors: temperature and shear stress, which is driven by fluid velocity. Once the main model data is loaded, you can run calculations for each pass individually. If field measurements, such as tube skin temperatures recorded by pyrometers, don't perfectly match the simulation, you have flexible calibration options. You can shift the entire temperature curve globally or apply point-specific adjustments. For example, here I'm manually entering a measured skin temperature for tube 19 in pass 3. Keep in mind, although we manually adjust the skin temperature to match field readings, the software internally converts this to the precise film temperature for each tube. This film temperature is then used for the actual coking calculations. The coking model constants are initially set to general default values. However, for higher accuracy, you can replace these with specific constants derived from laboratory analysis of your feedstock. You also need to specify the prediction period, the duration over which you want to forecast coke accumulation. After running the model, the predicted coke thickness for each tube is displayed. As you can see, tube 19 in pass 3, where we adjusted the temperature, shows the highest coking rate. Interestingly, no coke is predicted downstream of tube 22. Why? If we look at the velocity profile, we see a significant increase in fluid velocity in those final tubes. This higher velocity generates greater shear stress, which effectively inhibits coke deposition. Finally, if we choose to override the main model with these results, the predicted coke distribution is automatically transferred to the coke and fouling page for pass 3. We can then rerun the main simulation with this updated fouling profile. Finally, we arrive at Dr. Heater, the last analyzer in the suite. This is a highly unique, precise, and powerful diagnostic tool. It evaluates heater performance against key industry standards, including API 560, API 530, API 535, and other recognized design procedures. Essentially, it compares every aspect of your heater's operation against optimal and standardized benchmarks to identify potential issues. Let's see Dr. Heater in action. First, let's briefly review the real-world heater model we've loaded for this analysis. As you can see, it's a natural draft box-type heater with 4 cells and 6 passes, operating in a VDU, vacuum distillation unit, service. The convection section not only handles the main process, but also superheats 2 steam streams, LPS and MPS. The heater features steam injection, and the tube diameters vary, starting at 4 inches in the firebox and increasing to 5, 6, and 8 inches in the final passes. Once the simulation is complete, we load the results into Dr. Heater, specify the services for the tube banks and firebox, and run the analysis. The results are categorized by severity into 3 levels: notes, cautions, and alarms. Let's examine a few critical findings. Item 8 flags slug flow in several tubes, warning of potential vibration or mechanical damage. Item 10 highlights that fluid velocity in certain tubes exceeds 80% of sonic velocity, posing a serious risk of erosion. This mirrors the exact issue faced in the actual unit, which led to tube failures. If we plot the linear velocity against the sonic limit, we can clearly see that the velocity in the final tubes exceeds the safe threshold, confirming the root cause of the real-world problem. Item 12 indicates that the flame length exceeds standard limits. Thanks to FHinfinity's precise 3D geometry engine, we can visualize this directly in the 3D schematic. Item 16 identifies a peak process temperature issue, detailing the associated risks. Looking at the process side temperature profile, we see a distinct temperature spike in the 3 tubes preceding the outlet. In essence, Dr. Heater acts as a digital expert, a specialized consultant dedicated to troubleshooting, optimizing, and ensuring the integrity of your heater design.